Good morning, good morning. Welcome back. I hope we had a great break. We start today on page 15, so open to page 15 in the big packet. And while you're doing that, we'll take our look at the calendar. So here we are, November 27th. Today we talk about fractals and nature. Hopefully you found some interesting things in the reading over the weekend. Just want to point out again that the plan for Project 2 was due last time. I got a lot of plans, but I didn't get all the plans. So if you have a plan, just throw it in the folder. Just want to make sure you're thinking about Project 2 sooner rather than later. Officially, Project 2 is due on December the 11th, but I'll just remind you, you can turn it in at any point this semester, including the day of the final exam. But if you want an opportunity to do a revision, you got to get it to me in time for me to read it and provide feedback and give it back, and you have time to respond. So December 11th, if you are planning on maybe doing a revision, otherwise really any time, including up to the day of the third exam. As you can see, we've got very few days of new material left. Today, counting today, we have 4 days, 4 classes of new material. So, 2 weeks from this coming Thursday, that'll be the last day of new material for us. I do have one day built into the calendar just in case there's a snow day. I don't know that we'll have one, but we'll figure out something to do on that day if there's no snow day. The last day of classes for the semester is our review day, and then the third test is December the 18th. Any questions on any of that?
I just had one quick question about the project. If you're doing a research paper, what kind of length are you looking for? Is it a set amount enough to get?
It's more important to get the information in, but a ballpark figure is 5 pages. Okay. Other questions? Okay. The exam will be right here in this room. Yes. Okay, so let's go here to page 15 and we'll start towards the top. Oh, just a reminder here, there's a new photocopied thing on your table, so go ahead and grab one. That perspective reading is going to be in tonight's homework assignment, all right? So go ahead and grab one of those off of your table. Okay, so we'll begin with number 1. Can we start with Morgan? Okay, thank you. Greg? Okay, so let's take a look at this thing called the Koch snowflake. So you might have done some reading about this over the weekend, but here it is. You start with a shaded equilateral triangle. There it is in the picture, and we're going to call this the seed to give us the idea that it's the starting point, like we're planting a seed, and it's the very beginning of this process. And what we're going to do is apply a rule to this picture. And here's the rule. It's written in part B. It says to the middle third of each of the sides of the seed. So let me see if I can be really clear here. I could cut this side into 3 equal pieces, right? And on the middle third of that piece, so I'm now talking about this piece right here, and similarly I can cut this guy into thirds and this guy into thirds, and so I'm just focusing on the middle piece of each of the sides. And what I do is attach, says here, we take that the middle third and attach an equilateral triangle. We're just going to add on an equilateral triangle. So coming out of each of these purple things, we're going to draw an equilateral triangle. Equilateral means what? All sides are equal, right? That's actually built into the word. Equi, there's the equal part, and lateral has to do with side. So you just stick on little equilateral triangles. You don't get to decide how big they're going to be. It's decided for you. Whatever the distance is of that, well, that's one of the sides of the new little triangle. So you have no choice. You just have to make 2 other sides that are exactly the same as the first one. Okay, so you can see that down here we start with the seed, and then we stick on 3 little equilateral triangles in exactly the middle spots, and we get this new thing. And we're going to call that step 1. So first, does everybody understand going from the original triangle to this new thing? Okay. And now look at this new thing, this new shape, the star shape thing. It's a perfectly legitimate thing on its own. And so I'm going to take that same process that we did before and apply it again. So I'm not going to do it all the way around. But for example, take a look at this side right here in black. I'm going to cut it into how many equal pieces? 3, just like we did up above. Put them in green. 3 equal pieces that black line is cut into. And then I focus on which of the 3 pieces? The middle one, just like we did above. It says focus on the middle third, so that's it right there. And what do I stick on? An equilateral triangle. And is my triangle going to look like this? No, that's not an equilateral triangle, so get rid of that guy. Is the triangle going to look like this? No, I didn't attach it to the middle third. We need to just focus on the little tiny thing in the middle and put a little tiny triangle right there. And just as well on the next black line segment right here, we attach a little tiny triangle in the middle and a little tiny triangle in the middle of each of them. You get the idea? So every line segment you see, you find the middle third and you stick on a little equilateral triangle. And when you do that, the step 1 shape becomes this step 2 shape, more and more pointy. Is there a question back there, Gary? How come? Yeah, there's physical limitations to this. We can imagine doing this process forever, but physically there's going to come a point where the sides are so small that we're not even going to put like a little pencil dot and make a little equilateral triangle. There's just not enough resolution. So yeah, it's something that we can think about doing forever, but physically we do have some point where we just can't do it anymore. Lucas. Yeah, so let's go ahead and we'll look at the next page. And again, you'd imagine taking each of the little sides here. And so even here, I'm having trouble because of the resolution of this board. I can't even be that precise, but you stick on little triangles there. And we turn step 2 into step 3. You can see it getting pointier and pointier. And then step 3 to step 4, can you see a difference? You can, but you have to really be looking for it. And then if I were to show you step 5, I'd imagine it would look exactly the same as step 4. You'd only be able to tell them apart if you could really zoom in enough, if you had enough resolution that you could see the differences. All right, so let's go to Gary for part E. Good, that's exactly what Gary was talking about before. Alex, number 4. Okay, thank you. We'll go to Gina for number 5. Okay, so we haven't used the word perimeter in this class before, but if I tell you that the perimeter of this thing is 27, what does that mean? Yeah, 27 around. If you were to walk around this shape, measure all 3 sides and add them, you'll get 27. So because it's equilateral, they're all equal, you can tell me exactly what each side is. How long is each side? Here to here? It's got to be 9, right? They each have to be 9. It's the only way we're going to add 3 equal numbers and get 27. So, so the question is, what happens to the perimeter when I go from the seed to step 1? So now the perimeter is this piece right here. So I guess the choices are bigger than 27, less than 27, or equal to 27. Can you guys give me like thumbs up if you think it's bigger, thumbs down if you think it's smaller, and just to the side if you think it's equal, the perimeter of that blue star? Let's get everybody to vote. I see some votes. I want to see more votes. Is the perimeter of the blue star bigger, smaller, or the same as the 27? All right, so I see mostly people saying bigger, and I think that's true. If we take a look at, let's focus on, say, this side right here, the green one. How long is that? Definitely 9. Now that side came, like it used to be here, but instead of the green, we now have this thing and this thing, plus these 2. So the question is, which of those do you think is bigger? The black 4 pieces or the green, the one long line segment? Morgan? Yeah. Did everybody agree? Like we've pulled it out, right? Green was straight. That's going to be the shortest thing. If you pull it out at all, it's going to get a little bit bigger. Okay, so it gets a little bit bigger. So maybe the new perimeter is like 30 or 40 or something like that. And then when you go to step 2, how does the perimeter of step 2 compare to step 1? Bigger, smaller, or the same? It's going to be bigger for the same reason that we had before. So every time the perimeter gets bigger, the question is, does it get bigger like forever, like infinity bigger? Or does it get bigger but kind of level off? You know, maybe it'll never get bigger than 100 or something like that. Morgan. Okay, Morgan is skipping ahead to an important conclusion, and we're going to pretend he didn't say that. So let's just think about intuition. Suppose that you know, you're walking around like this is a lake here, and the blue is water, and you're just going to walk around this lake, and you're going to follow the curve, the path of the coastline, right? And the question is, how far are you going to walk? But now pretend it's not step 4, it's step 100. So it's really far out there, but you know, like we can't even tell the difference between step 4 and 5 looking at this picture. So do we think that the perimeter is going to get big without bound, like infinity, even though I can look at the whole thing? Is that going to be infinitely long, even though I can see it from this vantage point? Or is it going to like never get more than 100 or 1,000 all the way around? So that's one of the questions we're going to answer today. And now let's take a look at the next part. We'll go to Patty for number 6. Okay, so same idea as before, but now we're talking area. So I'll erase this thing here in the middle, and we'll put that the area is, what did I say? 30, 35. So if I say the area is 35, when you get to the next stage, is there more or less or equal amounts of area in the step 1? It's definitely more because we added, right? We still have the original equilateral triangle. It's still there, plus 3 new little equilateral triangles. And then step 2 has more area than step 1, and 3 is more than 2. So same question as before. If I could imagine carrying this process out forever, would I be looking at something that has infinite area, even though I can see it? Is there infinite area in that picture? Or does it kind of level off and maybe it's never bigger than 100 square units? Another question we're going to answer today. So let's come down here to 7, and we'll go to Danny. Okay, so we've got this picture on the far left. You've got some piece of the Koch snowflake, very bumpy. And then we focus on just one little tiny part. And then we zoom out, and what does it look like? Looks like the thing that we were looking at before, but it's not. It's only that piece. So this entire circle here is really just that little circle blown up. And so then we focus even more. So it's going to be hard for me to identify what we're looking at here. But now if I focus on zooming in on just that part, I think I'm really looking at maybe just like just a little tiny circle in the middle there. It's gotten bigger there. It's now zoomed out here. And what does that look like? Same thing that it looked like before. So no matter how much you zoom in, it just keeps looking exactly the same. And so that's this idea of self-similarity. It continues to look the same as you zoom in more and more. So here's a neat clip we'll show you on YouTube. And it is here. And I'm going to pause the video, but anyway, if you check out this video later, you can YouTube that. So we're back here on number 8. We're going to Stephanie. Okay, so what that means is that the similarity goes forever, whereas things in nature, we're going to look at a few pictures on the next page. But if you zoom in on something in nature, eventually you'll get down to like molecular level, and it won't look the same as it did originally. Universal means everywhere you look on the Koch snowflake will look similar to anywhere. And exact means it's perfect, whereas in nature things aren't often exactly the same as each other. So here's some pictures. They don't look so great on the photocopied handout. So look up here. What is the first picture? That's a fern. So what are we talking about with this self-similarity? Well, suppose that I didn't show you this entire picture, but I just kind of photoshopped, not photoshopped, but maybe I just got that part of the picture and cut it out, and I showed you that part, and I said, hey, what's this? What would you say? You'd say, oh, that's a fern. You wouldn't say, oh, it's part of a fern, right? You just look at it and say, oh, it's a fern. And if instead I were to show you just this little tiny piece here, but it's not tiny anymore, I'm blowing it up so it looks normal size, you'd say, oh, look, a fern. Now, eventually that breaks down. I can't do this infinitely many times, right? Eventually it stops looking like a fern. But the idea is that that's an object that appears in nature that has this self-similarity property. Here is a really interesting vegetable. The name of it is down here. It's called the Natalino romanesco, and it's a broccoli cauliflower cross, like a hybrid of those two plants. It is edible and apparently delicious. Looks kind of frightening to me, but there it is. And on the top right picture, you can see we're zoomed in. And, you know, like what would you say about like this little guy? It looks an awful lot like the entire plant that's in the bowl. And if I were able to focus in and really, really focus in on that thing, but zoom, you know, like zoom in so it's bigger. Oh, look, it looks like the entire plant that I'm looking at. Down here, anybody know the bottom left picture? What is it? That's a fiddlehead. It's another vegetable, also edible. And again, if I were to just show you, like if you knew what that was, but instead I just showed you that little thing right there and I zoomed in, you'd say, oh, look, it's a fiddlehead. How about the next picture in the middle? So it looks like some kind of a coastline. I can't tell. Maybe that's ice or maybe, I'm not sure exactly. But, you know, but we've got this coastline. And if instead I were to zoom in on, say, that part right there, make it bigger, blow it up, it would look like a coastline. And so you guys have seen lots of things like this where if you just keep zooming in, it kind of looks the same. And then finally, the last picture is, of course, some lightning. And if instead of showing the entire thing, I were to just zoom in on this piece and I'd say, hey, what's this? You'd say, oh, it's a bolt of lightning. You wouldn't say it's a branch of a bolt of lightning or part of a bolt. You just say that's a bolt of lightning. And the same kind of thing here. If I just showed you that, oh, it's a bolt of lightning. Like that. Okay, so just a few places where this idea of self-similarity pops up in nature. So here's what we're going to do for a bunch of this class is we're going to work on this snowing activity. And here's the goal, a couple of goals. So a couple of goals for this activity. Number one is to get you guys to actually draw from scratch the caught snowflake in several iterations of the thing. We already know what it looks like after 4 iterations, but still there's something to be gained from drawing the thing. And then we're going to start getting some information about how many sides the caught snowflake has and the length of the sides of the caught snowflake. And we'll really start thinking about numbers and formulas and things like that. So what you are going to do is follow the steps here. We'll do the first step together just to make sure we're all started in the right place. It says in the center of the triangular grid paper on the next page, you're going to create a seed triangle where each side is 9 units long. So here's your triangular grid paper. And I'm just going to pick a point that's somewhere towards the top middle of this page. I'll show you where I am, someplace up there. And that's going to be the top vertex of this triangle I'm about to create. And so what I'm going to do is I'm going to count. I'm going to put numbers on mine, but you don't need to put them on yours. I'm going to count these sides right here. So that's 1, that's 2, 3, 4, 5, 6, 7, and I've got to keep going a little bit, 8, 9. So go ahead and count 9 away. So just 9 little line segments. Be really careful when you count because you don't want to be off by 1 and then 3 steps later realize that the whole part of your picture is messed up. And how do I find the other part of my triangle? We're going to count 9 again. So I'm going to count on the bottom. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's right there. Probably should have started by saying this, but you're going to want to use a pencil for this exercise. So see if you can find a pencil, and if you don't have one, maybe somebody at your table can lend you one. I have just a couple of rulers that I'm going to pass out, but somebody could use the folder on the table and just any kind of straight edge you can use. And so just go ahead and draw as accurately as you can, draw the first version of the triangle, the seed, and then follow the steps on the previous page. It tells you exactly what to do. So what I'd like to do is, I feel like everybody's got numbers in the table and they've got some nice pictures drawn in, and then we get kind of stuck when we get to page 20 with these questions. So the first one says, find recursive and explicit formulas for the number of sides at step n. So the number of sides, first of all, the formulas that we're going to use They were all P sub n. I think a lot of people went to page 12 to find formulas for recursive and explicit stuff. Here we have a number of sides. Here we have the length of one side, and finally we have a perimeter. I'm going to use P sub n for the perimeter. So I'm going to use something different for the number of sides. I'm going to use S for the number of sides. And I'm going to use L for the length and P for the perimeter, just so that we have different letters for these guys, okay? So here's the idea. Back on page 12, you refresh your memory, we had two different kinds of ways that things could grow, populations could grow. You could grow linearly, or you could grow exponentially. For linear, you were adding the same amount every time. For exponential, you were multiplying by the same amount every time. And I'll fill in just a few things here in my table. Number of sides for the seed was 3, and then the number of sides in the next step was 12, and then 48, and then 192. Yes? To get from one row to the next, are we adding the same thing every time, or are we multiplying by the same thing every time? We're multiplying. So the version of the formulas that we're looking for are the exponential. Those are the ones that say multiply by the same thing every time. So I will remind us of the two exponential formulas from page 12. One of them said Pn is equal to Pn minus 1 times the common ratio. You'll find that exactly like that on page 12. And then the other version of this formula said you take your start amount and you multiply by the common ratio to the n. So those were the two different kinds of formulas we saw back on page 12. The first one is the recursive one. Second one is the explicit one. So let's see if we can't use those two formulas here in number 1. So we're going to do the number of sides and put it here. All right, instead of Pn and Pn minus 1, what letter are we using for number of sides? Instead of P, we're using S, okay? So that formula just changed the P's to S's. Sn equals Sn minus 1 times, and then we're about to fill in the blank. But we're just changing the number, the P to an S, just so it's number of sides. And then we need to fill in the common ratio. The common ratio is just that number that you need to use to multiply to get from one row to the next. What do we multiply by? 4. That's the common ratio. So all we do is put times 4. And I know there is a level of abstraction here that's going to make some people uncomfortable, but I want it to be more than just formulas that we're copying rote. Here's what it says in English. If you want to know what to put in the current row, n is what we're just calling a generic current row. You take the number that was in the row 1 before, just take the previous number, and you multiply by 4. Isn't that the pattern? Just take the previous number and multiply by 4, and that's what it says. Take the previous number, multiply by 4, that gives you the next number. Okay, and then if we wanted to use the explicit version, again, the letter P is going to become what for this question? It's going to become an S, so we go Sn equals the start amount. What was the first number, the seed number for this column? It was 3. Times, and then we're putting the common ratio in parentheses, and then you raise it to the n always. That's just part of the formula. And what's the common ratio for this problem? It's 4. So that right there is the explicit version of this formula. Sn is equal to 3 times 4 to the n. For example, if I were to replace the n with a, let's just say n is 4, for example. If I do 3 times 4 raised to the 4th power, I get 768. Was 768 the number in the 4 row? Okay, so this is a way to find the number in any row. If you want to know the number in the 5th row, what happens to this n? it becomes a 5, and you can just type it into the calculator very easily. 3 times 4 to the 5th. The next number is 3072. It doesn't rely on finding the previous 5 numbers. You just zip to any row that you want. That's why the explicit formulas are nice. Are there any questions on those two formulas there? Okay, so then what I'd like you guys to do is use the same idea, but try to answer number 2 here, which is the length, and try to answer the perimeter one as well, number 3. And there are a few other questions that follow. All right, so let's come back together. We've got a few formulas that we filled in for the number of sides, the length, and the perimeter. And we'll just get an answer up here. The 10th number in this sequence, we're going to use the second formula that's in purple, 27 times 4/3 to the 10. And I think people had 400, was it 79? Is that? Okay, so the perimeter there is about 479. If you keep multiplying by 4/3 over and over and over again, the thing will grow to infinity. So even though we could imagine looking at the infinite Koch snowflake, here's the step 4 version on the top right. You could imagine doing this process forever. At some point, it won't even look any different to us. But it turns out if you walk around this lake, it will be an infinitely long walk that you're going to try to take. If you actually had the full-on Koch snowflake, even though I can see the entire thing right there, the entire thing fits in this, like, like say there's a 2 square foot box I could put around this thing, no problem. Still, it's infinitely long if you were to try to walk around it, even though I can see the entire thing. It turns out that there's stuff that you can know about areas as well. Oh, let me be clear, just to make really sure that we're good on what we're expected to know. For the Koch snowflake, yeah, Morgan. Well, we wouldn't get very far. I mean, like, yeah, trying to get to like the next point, I wouldn't be able to even get to the next tips that I see right next to me, because there'd be infinitely many little teeny tiny curvy things right near me. So it's weird to think about. Okay. I mean, so you'd be moving. I mean, we could put Usain Bolt there, and he would run a long way, but he would appear to not move at all from our outside perspective. Okay, so here are some facts that I'm expecting you to bring with you to the final exam, either up in your mind or on that little cheat sheet you're going to prepare. For the Koch snowflake, if you want to know how many sides you have, it's always multiplied by what? 4, always. You guys figured it out today, but it is a fact, so you're welcome to put that fact on your little formula sheet. For the length of each side, what do you always multiply by? 1/3. Every time we have a Koch snowflake. I could change things. For example, in your problem here, we started with a length of 9, right? Well, it doesn't have to be 9. I could have said this was a 15. But the fact is, it is always times 1/3. That is just a fundamental property of the Koch snowflake. So what's the next side? If it's times 1/3, next side is going to be 5. Right? And then the side after that is going to be 5/3. And then 5/9. So I can give you a different starting number, but the property that's still consistent is times 1/3. So this guy right here is always times 4. This guy here is always times 1/3. For the perimeter, what's the magic multiplier? 4/3, always. Fact about Koch snowflake. Okay, so it turns out that instead of thinking about how long the walk is, instead of thinking of how long the walk is, we could think about how much space is enclosed inside of the shape. And if we go back to our step 4 Koch snowflake up here in the top right, the area of the original maybe was a 35 square units. It's clearly the step 4 snowflake is bigger, it's more than 35. But the question is, even though it gets bigger every time, does it get bigger to infinity? Could I be looking at infinite amounts of area in that picture? And surprisingly, the answer is no. So let me pull something up here. This guy. So there's tons of numbers here. I'm going to try to make these bigger a little bit. So here's the idea. The original triangle has an area of just over 35. And the next triangle has an area of about 46. The next one is about 51. What's happening to these numbers? They're definitely getting bigger. But it turns out they're getting bigger by less and less. When you add more triangles, you're adding a lot of them, but they're tiny, tiny, tiny things. And it turns out as you look down this row, What do you notice about, say, those two numbers? How different are they? 0.0007. You're not adding a whole lot of area when you get there. And here is one more fundamental fact. We'll leave you with this, and I don't need this to go on the formula sheet. I'm not going to ask you to memorize it. But it turns out that if you take the original triangle and you multiply by 1.6, always 1.6, that tells you what the area of the infinite Koch snowflake is going to be. You don't need to know that for the test. I'm just sharing. Okay, have a wonderful day. Homework is in the usual place. And again, you have a perspective handout that's going to be part of your reading.